Hello Hans, thanks for choosing me on instead. This video presentation will guide you briefly through the steps I have done. Next. So this was the data, your data in prices. Sheet 1A contains most of your data. Now you'll see I have done a monthly average of returns. And why have I done so? Well, let's plot returns. Wow, you can see that the scatter is quite volatile. However, this volatility band does not mean that the stock goes very up. Yeah, the next it comes down. Again, this doesn't mean he gets ruined. Well, the next period it comes up, and therefore you can see a long run. You can call this a seasonality. You can call it a trend. There's a seasonal fluctuation, and then there is a trend. There's a trend line if you can fit to it. And there's also cyclic fluctuation. You can see us. You can almost visualize these sinusoidal curves which fit this them. So this is too volatile. You don't want this. You would rather have something like this, which makes more sense, as now you have more season data and you can see the seasonal fluctuations and what happens, etc. Now this could be a monthly average because we know that prices move according to quarters. So this can be at the best at least monthly. This could be 10 days moving average, this could be 15 days moving average, this could be 30 days moving average, this could be seasonal average. So we have just taken a monthly average and we have fancifully done this a year or a month, and there is a formula for this, and then we proceed to the mean of returns, which is the average of the monthly averages. You can see them. Well, we are done with this. Yeah, so this is the formula for mean of return, this is the formula for standard deviation, and this is the formula for value at risk. This is the normal formula for value at risk. So what is value at risk? Well, it's the value you can lose when you put your this amount of money, 10 to the power 5, 10 to the power 5 in this particular stock. So how do we do that? Well, this is a Z value. This is a critical Z value. This is obtained by we are given the critical .9999 percentiles, and then you have the mean, you have the standard deviation, so you have the critical value of Z, and then you multiply it by 10 to the power 5 to get the value at risk. I do it for all 4 stocks, and this is the minimum. This one, yeah, I've highlighted it. I copy this sheet to sheet 1b, so you can see the individual VARs are there, but they have nothing to do with the statement of the problem per se, which requires us to find this. The VAR of the new portfolio constituted by 25,000 each of all portfolios. So now we know the ratios of each portfolio. These are equally weighted portfolios. Now, given I know the weights of each portfolios, I can calculate the covariances of each portfolio. So given in the columns A and B, you get the variances. So what are the variances? Well, L3 to the power 2, and what is L3? It's a standard deviation. So the variances are the square of the standard deviations, and so we get the variances, and then we have the covariances. So if you look up Wikipedia article on sum of variances formula, then you'll find that sum of variances equals to, well, the sum of the individual variances multiplied by weight squares. So it's equally weighted here. If it wasn't equally weighted, we would have to multiply it by the weight square, and then covariance of each of them, Ford Motor and GM, which would be alpha I into alpha j into covariance. If these things would be alpha I into alpha j into covariance, we wouldn't have covariance here. So it's effectively writing 1 into covariance, and then we do a sum over all of these. So here we land 2 into sum of these in red, and this could be 1 into 1 or whatever. So 2 into sum of these in red, and 2 into sum of these in blue. Sorry, sum of these in blue, which is the sum of the variances, plus 2 into sum of. This is the formula of standard formula, and then we back out the standard deviation. So we calculate the VaR in the similar fashion in which we did in 1A, which is the standard this from the normal distribution. So finding out the percentiles of from the normal distribution given the mean and the ST. So into ST into 10 to the power 5. So now we have again 10 to the power 5. We have the this 1.01, which is the point 1 minus 0.99. This is the mean. B15 is the mean. Well, what is the mean? It's the weighted average of all means. So since it's equally weighted, it's the simple average of all means. We have got the standard deviation, which is square root of variance, which we have obtained by summing up the variance and twice of the covariance, weighted covariance. So it's a simple covariance terms, and then we multiply this standard normal, sorry, this normal inverse. We have not standardized it. We multiply this by 10 to the power 5. And now what's the relation of this number with these VARs. Remember, I just said that there is a relation. Well, if we add up these VARs, we will get something which is more than this. Then we will call it the diversification benefit. And what is it equal to? This minus, how many stocks did we have? We had 4 stocks. So 4. This is a smart way of doing the same. Oh. Hmm. Sorry, this is not as. So you can see that we have computed the diversification benefit. Well, it seems it's not it's not wise to, well, it's wise to diversify. Actually, this is less than the sum of these. So if I had to do it in 4 independent stock, this variance, it would be this much minus. So we see that this is always less than the sum of weighted VARs of the portfolio, and this is known as the diversification benefit, the amount by which this VAR is less than the value at risks of the 4 portfolios. However, this wasn't asked. So the next question, we are asked to find VAR using value at risks using the exponentially weighted moving average. In 1b, we were doing the variance covariance. So how many number of covariance? For a tally, we have to know we had got 1, 2, 3, 4. So 4C2, 2 at a time, right? Weighted covariance, 2 at a time. So 4C2 equals to factorial 4 by factorial 4 whole divided by factorial 4 divided by, in brackets, factorial 2 into factorial 2. That gives us 3 into 2, that's 6. So let me see, 1, 2, 3, 4, 5, 6. 6 covariance terms. So this, thus we know, using the C2, 4C2 for 4 more 2's out here, we know that we have covered all cases. Well, now in 1C, we can see the value at risks. And how have we calculated that? Well, this needs explanation. This formula you can see. Well, first things first. Exponentially weighted moving average cannot be done on monthly averages, because exponentially weighted moving average devalues or ignores further observations distant in time at a very fast rate. You see our weights have long boiled down to 0. So even to keep it somewhere around 0.1, it's 115. Let me just see where 115. Well, I don't even span 2014, so there are issues if we try to do this with monthly average, and it's done with daily averages. So that's the concept of exponentially weighted moving average for. And now we see how we calculate the weights. We have calculated the weights as 1 minus 4 into this into count. Well, this is a very mechanical way of doing this. We could have also done this by into 0.94, that the upper one is to the power 1 minus 0.94 into this is 1, right, count, and then we can just go on. So you can see that these are all we haven't just deleted the columns, we have kept it, but we haven't used these monthly averages. In this sheet we have got the weights and now the r square into weights. You can see the formula there. This is the r return square into weights. And then the interesting part is that each of this, for example, K3 equals to lambda, that's 0.94 into 1.17 plus 1 minus lambda into 0.001082%, which means this is equal to lambda into this plus 1 minus lambda into this. Well, lambda is 0.94. We are almost there. Once we have come here, thus if we had to project one period ahead, the next period's volatility would be equal to, well, 0.94 into h square, that is the return square of last period, plus 1 minus 0.94 into K2, which is our twin to weights. This gives us the volatility, and when we take its square root, we take its return, we get the return back, or log of return back, and then multiplying it by this could give us a number which is greater than 1, but we are interested in, taking the exponential of this could give us a number which is greater than 1, but we are not only interested in a gain, we are interested in the loss. So if a equal gain is possible, a loss is also possible. It's a kind of a walk, right? So it can be in any direction. So loss is also possible. So the highlighted field is the field which tells us about the next period's volatility, and by backing it out and carefully multiplying it by and taking the abs of it, we take the value at risk, the maximum loss possible. We have done this for all these, and then I proceed to D. In D, you see the term EVT. What is EVT? To explore this, we have to go to this, where we have these histograms. The extreme value transfer form is the value, this is the distribution of the realized distribution of values which are greater than a threshold. So in our problem, we have the VaR with u equals to 2000. So we are more concerned with distribution of points which have a loss which is greater than 2000. How do we do it? First, this formula, study this formula carefully. This says this is the value of loss. This is how I would say it's loss. It's the next period minus this period. If this is less than minus 2000, then if this is less than 0, it's a loss, and if it's less than minus 2000, then I'm talking about extreme value transforms. I'm talking about values which I consider extreme, or tail values, tail events. So these are the events I'm getting serious about, and I say if this is greater than or equal to 2000, it's 0. Let's take the negative of it. I want the loss in positive terms for things obvious soon. Why take the 0? Next. Well, I will soon do a filter on this. The filter did not get applied. I'll again, once I have the filter, I can just churn out the non-plausible or non-necessary things I am not interested in, and then I can just copy this and paste it. You can see it's already pasted, and then I can remove the. Now you can see I have taken some bins. That's simply to take the histograms. I'm going to elaborate on. Let's see what I've done. This is the percentile. So basically, like, since we have to correlate the concept of the extreme value transform to the concept of VaR, we are taking the beans at the percentiles. So that, let's say I wanted to get an extreme value such that it's the median value. At least 50% of the observations will lie to the left of it. So I want to know what's the median. Given that it goes above 2000, what is the median loss? Because this could be different. The distribution of these points, since these are outliers or tail events, their distribution could be quite different from the distribution of the original distribution. So when we are talking about value at risks, these distributions need to be studied separately from the VaR. The concept itself is different. It can be developed and it can be studied as a different distribution, but now we are here to drive this problem to its logical conclusion, and therefore, well, I can choose my percentiles. Now let's say we don't have a 50%. Well, we don't have a 50%. Yeah, we don't have a 50%. We have a 51.85, but then it's a bit far. We have a 29.63, but then it's a bit far to the left, so we know it's somewhere in between the 2 points. So if I were to cluster it, it would be in the in this point and not here, because that point is included in this point, this bin. Well, I can even spread it out over more and more points, but here we are to study how to do it. Obviously, we won't get a smooth thing every time because we can already see we have 28 points. So that's as far as we can get. But in bins, we usually do finish 10, 11, 12. So it won't be a very smooth curve always. Here it could be a smooth curve, but then again, as I told you, it's just for. So let's say I need a roughly 60%, 0.60% tile of tail values such as 0.60 lie to the left of it, and given that it crosses 2000, a loss of 2000. I want to study this event separately. So this is the point which is 48.15, this is 62. So I guess this is somewhere around here. We can obviously do a linear average of these 2 points to arrive at it, but this is good enough. Now I can also talk about the expected loss of the mean, that given that a tail occurs. This is 2913, but again, you are more interested in concepts like volatility, and you are interested in concepts like VaR. So the only way to logically reconcile VaR with the EVD extreme value transform or the extreme value distribution returns is by binning. So how do we conclude? Well, this should make sense. Value at risk with a tail event located at 0.6 percentile, given that the loss is greater than 2000, is equal to this. We can also talk about the variances and the kurtoises and other skewness parameters of this distribution. And by VaR, we could talk about the mode, we could talk about the median, we could talk about the first quartile, we could talk about the last quartile, we could talk about the mean. But here, since we have to reconcile the two concepts, I have drawn this to the logical conclusion. Please do this for this as well. I have just done an expected loss. So let me keep it. So again, VaR at, you won't like a big VaR when you are studying this, because we are already short of data points equals to 0.6. So 60% roughly here. Yeah, 62.96, perfect. And it's 6862867.59. Well, Hans, thanks for being with me, bearing with my lesson so long. It's late night here at India. Thanks for connecting with me on Instadu. I am your tutor Subhrodip Sengupta, and I hope to help you again very soon. Thank you.